Hey folks, thanks for joining in. Today we have our guest Nikhil, who is also joining our podcast today, and yeah, Piyush and Rajat uh, is also in meeting. So the today's topic is we are going to discuss about how's the day look like for embedded software engineers, and yeah, whoever wants to jump in uh, can start.
Well,
Okay.
actually, maybe let's first have Nikhil introduce himself, and then let's
Yes, of course,
let's
yeah.
start with Nikhil. Go ahead, Nikhil.
Okay. All right. So, hello everyone. I have been into the embedded industry for around 12 years. Okay, my name is still showing as Infinity, so I should say my name is Nikhil because people might not know that.
Yeah.
Yeah. So I'm Nikhil. I've been in Bangalore for close to 12 years now. I spent almost a decade working in Texas Instruments. I worked on like Linux kernel and things like so. All my embedded experience is coming from there, and it's been last 2 years. I have joined Google, and all of these folks are now my colleagues.
And how does your day look like?
Yeah, sure. So now we'll start.
Yeah.
I would not answer really like from a day's perspective because you can say it's not like every day I start on a new project and by end of the day I'm like done with it. So you can say that for a longer time, maybe like a quarter or something, we are kind of working on similar project. So rather than answering from a day's perspective, I would like to answer like how exactly like a typical project goes through, because a lot of people might be interested in how embedded development happens. So
Right.
typically, when you want to like make an SOC, somebody at the management pitches that okay, let's make an SOC, and here are the features it should have, and here is what you would like to sell it at. Here's the target market. It gets approved. Now, at that time of when that happens, you also want to start including the software folks at some point of time, even before the SOC is manufactured. So we call that phase as pre-silicon phase. So there's a phase where somebody from the architecture side they decide this is what the SOC they need to do.
And the
But
architecture in this case is the hardware architecture.
correct, the hardware
Yeah.
architecture, correct.
Okay.
But
Go ahead.
then once the SOC is like in a phase where we now know that okay, some pieces are together and then software can be run on it, but we don't have the SOC yet. So one option is we either make the software team wait for it, and then once the SOC comes back, you run on it. But then there's a lot of risk on it because
Hmm.
once the SOC is manufactured, it's done. You can't really do anything, and that's where the pre-silicon phase comes into picture, where even before the chip is manufactured, that we try to run it on like emulation platforms and make sure that the software runs on that work in progress SoC. And there we are kind of making our software ready, at the same time also trying to identify issues in the hardware, and that is a really crucial phase to the
Hmm.
success of SoC.
Go ahead.
Yeah.
Well, when
So
go ahead.
just to put a number to it, I think Hansen, NVIDIA CEO, did talk about this. That what is the cost of mistake in silicon? So just to put a number, so whenever a silicon is ready as per design, the foundries try to prepare a mask that they are going to put on the die. Preparing that single mask costs you millions of dollars, and a small mistake in that mask means you need to remanufacture that mask, and that mask is again going to cost you millions of dollars. So that's why you have to find all the things
Yeah.
that you want to correct it even before that mask is built. So you
Yeah.
cannot wait for the SoC to get manufactured.
Missing a connection there. It's like, oh,
Exactly.
oops. This where
it,
does
it
this wire go?
that mask cost, at some point that
It's
mask cost
expensive.
exceeds your engineering cost.
Yeah. But it's a non-recurring cost, right? You make it once, and then for the lifetime of that one particular silicon,
Yes,
it just stays.
exactly.
That also reminds me, the mask is getting smaller and smaller and smaller with every 1.5 to 2 years.
Yeah.
Moore's law, right? Okay, we just agreed on that.
Yes,
So nice.
yes, Nikhil. You can continue.
So
Yeah.
kind of this is little bit of unintuitive because the software philosophy is fail fast. But in the case of hardware, we can't really do that because if we fail to make the SoC right in one go, it does cost extra, as uh, uh, Rajat said. So we want to make
Cost
sure that,
cost of iteration is very high.
yes, and that's why we want to make sure that there's enough effort spent on the pre-silicon aspect of it.
Right.
And then, like, once the SoC is manufactured, then we basically get into the normal embedded stuff that people are aware about. Like, you look at a board, you try to run a software on it, and then there are challenges with respect to working with the limited set of resources, like less RAM, less storage, less latency, and whatnot. And you need to make sure that you customize the software to, run it on. And then,
Mm.
depending on the use cases that you have, there is always scope for adding new support or optimizing something, making better performance and things like that. So at a high level, if I have to explain the project, it's like there's enough work spent on the pre-silicon part. Then once the SoC is made, then you basically kind of start running your software. And typically, this terminology is very common in people who are working in the embedded field. There's a
Right.
term called bring up, and
Right.
Fish, you want to talk about like your bring up
Oh yeah, yeah,
experiences?
yeah. Well, I suppose I've had this good fortune of working on bring ups of lot of SoCs. I'm saying lot, but it's like two to three of them, right? At like a professional level, and then at home, on boards and like the hobby boards. Of course, I've done it many times. But the idea of a bring up is that you get this chip from the fab, and the idea is to, you know, piecewise in a very modular way make it boot up to the functional state. And the idea is that at each stage you're using like, or rather, you're trying to execute your software which has least amount of dependencies. Okay, I'll just elaborate in terms of what this means. So let's say you get like a silicon from fab. Now the first thing you would want to do is ensure that things are powering on. So there is like a sequence that you execute, or certain hardware that you activate and see whether or not the voltage rails are right, so on and so forth. Once, let's say, that is right, the next stage would be that you allow uh, kind of the power management chip to go ahead and turn on certain other circuits on the board. And then slowly, once that goes through, some part of the circuit will kind of boot up your processor, or rather, power it up and let it go free. And when you're booting up that processor, the idea is that you should have this minimal software, or software with minimal dependencies, like just a UART memory and the processor. So only three components involved, and then you see that, okay, these three are functional, the CPU seems to be doing what it's supposed to do. And then you load like much more complex software stack on it, and then check whether or not, turn on the caches, check whether the caches are well behaved, so on and so forth, to the point that you have turned on all the pieces on the system, and now you boot up something like maybe Linux and Android and so on and so forth. So yeah, that is fun to do, uh, but it is full of moments of existential crisis. Every once in a while, you would not know if the hardware is misbehaving, your software is misbehaving, you are the one who is an idiot who could not flip a bit, some weird thing. Yeah,
Yeah,
but
I can
after,
relate
yeah,
to.
go
There
ahead.
are cases where I remember, like, I was prepping one of my team member to go for a bring up, and
uh,
I was telling them that, when things go wrong, you're allowed to doubt that your software is wrong. You're allowed to doubt that this specific board that you are working is wrong.
Also
This
wrong.
specific chip that you are working on is also wrong,
Would also
or
be
maybe the general hardware design is wrong,
wrong.
and there is a good chance that any one of them can be right.
Yeah,
So
Yeah.
typically, that's the case.
and it's full of those moments where you sometimes feel like a god, and sometimes you just feel like a complete moron. It's like, okay, 5 days and I forgot to flip that bit.
Hmm.
And typically, almost always, like, you'll be stuck with like a problem for like a week, maybe, like it's heating up, everybody is like now focusing on that, and some senior junior somewhere completely unrelated passes by, sits down with you and says, huh, okay, you forgot to mask this bit or enable this bit, and then it's like, yeah, okay, thank you.
Uh, amazing thing is you forgot to flip the UART dip switch. That's why the
Okay.
UART was not coming on the
Yeah,
and you realize it on the fifth day. Till then, you are
yeah,
debugging why UART
yeah,
signals are not coming out.
yeah.
I've seen
Yeah.
cases where, like, I don't know if it is common or not, but like TX RX got swapped on
Oh
creating
yeah.
the board. Yeah, everywhere this has happened. Like so many times
Well,
I've seen.
because that's a problem with the industry. Till now, industry has not standardized how TX and RX should be connected. Some manufacturers do it in a
TX to
reverse
TX.
direction. Some manufacturers do it one to one. So when you get a UART to USB converter from outside, and when they say TX and RX, it can mean anything. It can mean they wanted you to connect the TX of the that to this, or they can mean that you were supposed to connect the R. This is the TX of this device. You are supposed to connect RX of the that to this.
Other
Right.
So you
device.
have
Oh,
to
I
Yeah.
go
never
back
thought
to
of it
the
that perspective. Yeah, thanks for bringing it. Basically, you are trying to say that TXRS is relative and
Relative
something
to
exactly.
the
is bound to
device.
happen. Okay.
Yeah.
So you have to always go back to the manufacturer and understand what do they mean by that TX and RX. Do they mean TX of the DUT or do they mean TX of this device?
By the way, just
Mm.
for those who don't know what that is, it's device under test. Yeah. Go ahead, Rajat.
Yeah, I didn't know that, man.
Yeah, this has happened.
I know
This
that.
usually the first practice that I do. I usually first I figure out what is the TX and RX of my device, and whenever this doesn't work, I just connect TX to RX on my device and see if I get what I'm typing, and then I blame that okay, this is the reverse one.
Mm.
Yeah. Okay.
And over the time, this has become my habitual. If UART doesn't work for me for the first time, I first reverse the TX and RX and then try something else.
The problem becomes even more confusing when you also have some mux settings to be done for the UART when it is multiplexed along with other peripherals. Then it's like, okay, my output is not going on the UART. Did I mux it correctly, set the configuration correctly, and then did I connect the wires correctly? And then still further, does the host, like the recipient of those messages, typically a Linux system, does it have like hardware flow control turned on? Like all of those awesome things.
Yeah,
Yeah.
so interesting point is that nobody pointed out how slow the pre-silicon development is
It's
in embedded system. Like typically, what happens is a software engineer, make some changes and instantly they can see over
yeah,
the
typically, yes.
platform, right?
Instant
But
gratification, yes.
yes, yeah, but in embedded world, what you do is you write certain changes and then you wait for let's say half a day or something, like depends on the resources,
And then a
and
print
then
of show,
the
shows
printer shows up and you are like, okay, my prints are going in. And then interestingly, if you have something messed up, then your whole the half day is wasted and now you are again starting at the same point, right? So
yeah.
these kind of situation happens, and I have run into some situation where I have made some changes and flashed it on the the emulation platform and then waited for half, let's say an hour, and then after that I realized, okay, there is something I need to change again.
Yeah.
And so I have to go through that process again. So I
This,
think
yeah.
making mistake here is also cost you a lot of time,
In the
and then resources.
pre-silicon, yes.
Yes.
Also, pre-silicon, there are many different platforms
Right.
depending on what stage of the development you are in.
Hmm.
Like the hardware folks use something called well, they use simulation, which is
After
like
information.
dead. Yeah, RTL simulation. That's like deadly slow. Run any software on that, and well, depending on complexity, of course, takes away half day to 2 days to 3 days also, just to get like the waveform dump, so on and so forth.
Right.
It depends what kind
Yeah,
of
it
simulation
depends.
are you running. If you are
Yes,
running a zero delay simulation, it's still fine. But if you are at a
gate
stage of gate level simulation, you are dead. Like I still know like Microchip used to manufacture small devices, and even they're running small microcontrollers, and even their running gate level simulation was a week's task. To get a result
yeah.
of a test out, it used to take a week. So the GLS was always left out whenever they wanted to debug some clock synchronization issue. Else, they always rely on a zero delay simulation.
Yeah.
So I want to point out one thing that yes, we have all seen that cases where simulation makes like it is slow, and we have all kind of changed our habits of how we work with emulation.
Mm.
So I wanted to point out that like typically
Mm.
when you want to like let's say you have developed a program and like now it is time to run it. Typically, a software engineer will be like, okay, ठीक है, let's let's try it out, चला के देखते हैं क्या होता है.
Mhm.
But you
Yes.
can't really do that when you are working
Yeah.
with emulation. You have to make sure
Iterations
that
will
you
cost
read
you.
your code. You read your code second time. You make sure
Right.
that it works. If there
Yeah.
is any kind of simple software-based simulation, you check that. Because
Yeah.
last thing you want is you are working with the emulation, waited for 4 hours, and then you realize, oh, you forgot to initialize a variable. You
Oh
don't
yeah,
want
yeah.
that.
That I've been there.
Yeah.
I've been
So
there, man.
the
It's
because the problem routes back that these systems are very expensive, so you
mm,
cannot have one lying on everyone's desk. So these systems are usually
shared.
time multiplexed,
Yeah.
Yeah.
and
Right.
you have a dedicated slot. And if you screwed up your 2 hour slot on it, the next slot you are getting is next day.
Working with simulation and emulation is a visit back into 1970s. Like
Yeah.
I've seen the hello world being printed like H E L
Yeah.
space O.
Yeah.
It's like, oh, there is a space. Yeah, that has happened. Well, one thing. Okay, I'll complete my story or my statements around the platforms. So simulation is like, at least as known to me, the slowest. Then there is emulation, is like the second slowest, like maybe 1980s equivalent. Then there is, emulators like uh, QMU and stuff, which are like little faster, and kind of, each developer can have one on their own desk kind of thing. And then after that, obviously there is silicon, which is like,
This FPGAs also. So
oh, there is
basically,
FPGAs also in between. Yes, FPGAs and silicon are
That's
like pretty much,
emulation. That's emulation.
emulation is a mix of CPU and FPGA.
You
And
can
again,
you can do mix and match, but
true,
ultimately that's
true.
what emulation.
Also, I think the slowness depends on the complexity of the
Yes.
silicon being emulated. That I
Right.
think is
on
fundamental,
an
because
average,
even
like for
QMU
the
is slower.
viewers, can we say that any pre-silicon platform is supposed to be 1,000 times slower than the
At least,
intended
yeah,
speed or
yeah, yeah,
something like
yeah.
Right.
Well, not supposed to be. It's like it is.
that?
It is.
In fact, people want to speed it up, and yeah, it cannot speed it up. Well, not cannot. They're having tough time. Yeah, let's put it that way. Well, that's that. And then I was also going to point out this, that even though the development cycles are slower, I think that's what also provides like a lot of space for going and doing a lot of research and learning on the side. Because even though you are like headed towards, let's say, production, if something's going to take 4 hours to boot up and print your result and run whatever that scenario, those 4 hours you can invest into, like, reading the source code, researching more about, let's say, the cache system, hardware, whatnot. And I've seen, at least, what is more, what is looking back, what I'm most grateful for is that, yes, it took 4 hours for things to boot up and run, but then I also got like roughly 3 hours out of that to go study something, like, maybe CPU architecture, C language, operating system basics. And when that thing either works or not, I can always go back, spin off another experiment. But yeah, I think the natural slowness or delays are induced in that process.
Mm.
And that way you're not kind of constantly burning out.
Other thing that also I noticed is, because you are working with kind of simulations or things being slow, you really kind of get into the small level details. Like when you
Yeah,
are working on a device driver,
yeah.
you check every stack, everything
Yeah.
that is happening. Like typically when you are doing a normal software development on a post silicon platforms, you just see that the interrupt happened. But
Yeah.
in the pre silicon platform, you say next, next, next instruction, and you see
Mhm.
everything, how operating system is handling interrupt, how it is
Yeah.
being dispatched to my driver, and all of those things you can really see in the code, like how your code is going through and whatnot.
Oh, that is true.
And that also gives you a way into like looking into the source code. Okay, this is supposed to be done or not, because you see if
Mm.
condition and it says that okay, I should, that the code should have taken if condition, and then you
Yeah.
realize okay, maybe it is expected or not expected and things like that.
True. Very true. Very true. If and I've noticed that when I worked with hardware engineers, right, and like the DV engineers, for example, they have their own set of tests that are written in C. They run it in simulation, and they used to run it in simulation. These people literally remembered file function names, approximate line, and they used like the tools like Vim and those kind of things, Vim, Emacs, where you don't have like
ID.
IDE kind of an environment, but they remember. And the thing is, when they used to look at my source code, they would like find out many different things, saying, "Hey, this line should have been here." That was bizarre. Like I've had so many learnings from them that way. But yes, it work of this nature forces you to slow down. This is definitely not the web development equivalent of let me change my CSS and the color instantly appear. No, sorry. Yeah, the
But
effort
I
to
also want to
reward is.
point out that even though we are saying that okay, the basically the amount of code we write is not much or something, the real joy is basically
Mm,
trying to figure out the specs and really write something which basically mimics it correctly. And when that interrupt occurs, you feel that okay, yes, I
done.
understood everything, whatever that was
Done.
meant to be, and the interrupt happened, and I've
Yes.
written correct code.
Yes.
So that really gave me like a lot of joy.
Hmm.
Yeah, definitely. And this kind of reminds me, people who are interested in forensics, this can be like a very good area of work for them.
Hmm.
Now, something's not working. Okay, work backwards. Take the spec. Okay, what are the preconditions? Are we meeting those? Should there be delays? Should there not be delays? All of that. Yeah.
So I would just like to say one thing. Uh, I think what we are majorly talking about is the semiconductor industry of the embedded and not
Yes.
embedded industry in general.
Yeah. Fair.
Yeah, so that people relate.
Let's
Some
talk about
people
the
might be
post
like,
silicon platform now, and then
Yeah.
exactly.
yeah, people should
Some
not feel
people
like
might feel
everything is
ये
pre-silicon.
ये तो मैंने जीवन में किया नहीं कभी.
Correct.
And
So
I'm an
this
embedded engineer.
semiconductor, these are all pre-silicon.
Yeah.
These are all pre-silicon side of things that we are talking about,
Yeah.
and there's a whole much bigger industry that works everything post-silicon.
Yeah.
Hmm.
That can be your Mercedes, BMW, and other product manufacturers or
Yeah.
OEM as the industry calls them, original
Original
equipment
equipment.
manufacturers.
Yeah. Yeah. I think that side is a lot more fun, just because it's like a lot more like the gratification cycle there is faster. Like you
Fast.
make some changes, flash on the device, boot it up,
And
execute
the
the
LED
scenario.
glows.
Yeah, and there it goes. Yeah,
Yeah.
and
So
They
so
they have their own
power.
problems.
Of
they,
course, of course. Like see
we we
the web.
we
Good.
we don't have to worry if our requirement matches a unit test, but an automotive guy has to track everything a requirement to a unit test to a
Yes.
development line.
Yes.
hmm.
Well, I was going to mention that, which area doesn't have its own problems. Like even the
Yeah,
web development guys have like the problem of centering the diff.
Yeah,
yeah.
that's a universal question, I think. Okay,
How
so
hard can it be?
so there is a question on the similar line. So like how do you see a lives of an embedded engineer is different from in these segments?
Mm.
The one being the we are working on a chip manufacturing, the other being let's say someone is working in automobile sector, one being health infra, one being working on, let's say,
Yeah,
writing
applications
drone
engineering, let's say.
applications. Yeah.
Yeah,
so
yeah.
So
so how
before
is that?
that, can we just conclude like we were talking about different phases of the
Oh, sure.
pre-silicon,
Go
bring up,
ahead.
and post-silicon.
Mm.
So
Sure.
I just wanted to clarify that even though we have been talking about pre-silicon phase,
Right.
it's
That's
typically like a
completely.
pipeline. So you are working on the SoC that got manufactured 3 years back. Then there is SoC that got manufactured like 1 year back. There's something that will be manufactured next year, and there will be something that will be manufactured maybe 3 years in the future. So typically there is always like a pipeline, and it's not like because it is 4 hours, I'm waiting for some software to be booted. I'm like free and like I'll just go have fun.
Have a coffee.
There will always be cases where you are working on production and like you're doing some real bring up while at the same time you are working on some pre-silicon platform. So that's actually fun because you're not always working on a slow platform. It's a mix, and depending on which phase you are in, there might be cases where for 6 months a lot of things are
Mm.
slow, but then things pick up very fast, and then you are
Right.
supposed to catch up with them.
Yeah.
Well, I just wanted
Well,
to
that
put that in the
that
context.
reminds me the amazing portion we used to be. So in my previous company, we used to have 6 design pipelines. That means 6 designs are going in parallel. And the interesting point will be when the tape out of one design pipeline overlaps with the bring up of the other design pipeline, and you are you are screwed up on both the parts.
Okay, that's
That's
Yeah,
a
that's
and it happens quite often. We may think that it happened by coincidence, but it happens quite often. You
but
might be in the bring up phase of someone, and might be in the tape out phase of something, and in the architecture phase of some other chip. So at a
yep.
point, there is a good chance that you might be working on 3 or 4 generations of the chip.
And then you have three meetings overlapping with each other at the same time. And you're like, okay, which one? Yeah, and so it's not gloom and doom though, right?
Yeah.
If you know stuff, then it becomes, very thrilling to do all of this. If not, then there is some senior that you see being thrilled by all of this, and then you learn.
yeah.
So that's what
Yeah.
usually happens. Okay, then should we now jump back to the question that Dave wanted
Yes,
to bring up?
yes.
Yes.
Go ahead, Dave. Would you like
Yes,
to repeat the question?
yeah. So my question was like, how does like embedded software engineer life differs in different sectors? One being the automobile, another being the, let's say, let's say AI and infra thing. Another being we are in, right, chip manufacturing. So how do you see typical embedded engineer's life is different in these different areas?
Hmm.
Like, what are the constraints, what are the good thing, what are the you know uh, uh, bad things?
Hmm. Well, I think I'll let Nikhil and Rajat speak to this.
At a high level, maybe I'll just give like categories and then we can expand it. I believe there are people who are solely working on microcontrollers where there is no
Mhm.
high level operating system and everything is closed source controlled environment and we get to do whatever we want. Then there are cases where there is like a very complex SoC with multiple CPU cores, mix of like microcontrollers and Linux operating system and things like that. There are cases where there is very less there's like a ASIC involved and you're trying to connect that ASIC to a Windows machine through PCI card or something like that, and you're supposed to be developing software that works with that ASIC. Then there are some field specific things. For example, people who are in automotive, they care a lot about safety, AUTOSAR, and certification and things like that. Then
Hmm.
there are cases where performance is like critical, like you mentioned about AI, where people are trying to build some AI chips where they want to squeeze as much performance as possible. And then there are cases where like end equipments, like somebody's building like a elevator system or like random things where like point of sale system and whatnot. So there the important thing is to like time to market and support and things like that, because they are directly working with the customers, most like small startups, embedded startups. They're just trying to like put out all the categories and then we can
Sure,
take
go
one
ahead.
by
Go
Right.
one
ahead.
and
Go ahead.
Yeah.
Go ahead.
describe about it, and feel free to
So
add more if I missed.
So I would present it like this. So this is actually a very big circle. So how the journey of the complete silicon starts is that all these marketing guys first go to all these OEMs and ask them, what are you planning to manufacture in next 3 years? What is your idea? Like what kind of products do you see? Maybe Cisco can say we see 20 switch 20 switch
Network switches.
20 port switches or some routers and gather all the requirements from them. What is your envision for the next 4 5 years? Because the reason for this is some of these chips have to work for 15 years, some of these chips have to work only for 6 7 years. There's a very different lifespan for it. If anything is going into automotive industry, that chip has to survive next 15 years
Mm.
Yeah.
without being reaching an end of life. So once all these OEMs etc. So marketing guys goes to all these OEMs, they gather the ideas, requirements etc. Like what do you want, and bring back into the semiconductor industry companies like TI, NXP, Microchip etc. And once these requirements are in, these companies start working on manufacturing that silicon for them. So this silicon, so you can think a typical silicon manufacturing takes around 1.5 to 2 years. This is the typical life cycle from inception to actually reaching the market. There's 1.5 to 2 years. So 2 years before people went out and asked, "What do you want to do in next 5 years?" You have already reached 2 years of that gap by getting that silicon out, and now this silicon has to survive next 13, 14 years as well. So it's a very you know very detailed process in which these OEMs predict, and the main job of these silicon companies is to stand their requirements so that these OEMs can success with their product. So the main job of the engineers sitting in these companies is to get this chip functional and match the requirements that the original equipment manufacturer gave to the company. So,
Hmm.
for example, some company can
Verify.
say we want a 12-bit ADC with this much precision. So, when the silicon
Mhm.
comes out, a lot of exercise will go around characterizing that ADC because that's the main selling point for that chip. So, similarly, there will be multiple selling points and multiple infra points that should be there, and then there are selling points because of which the OEM is going to buy for it. But the main job of the embedded engineers sitting in these companies is to prove that their silicon is worth considering for the OEM.
Right.
And once the OEM goes back and reviews the silicon again, that this was our original requirement and this is what you manufactured and gave to us, let us analyze if our product can fit on this. Once they take After that, the whole embedded software, what application should be built on top of it, what should be done from it, is taken over by the OEM embedded engineers. They will
Right.
go around, port the AUTOSAR, develop applications, maybe build a dashboard, the automobile dashboard. For if you are industrial, maybe build some robotic arm out of it, build a complete automation out of it. So that's
Blink
the
and
typical
LED.
software life cycle.
Yeah. No, I was going to. Well, I said it. Blink and LED. As part of all of that, somewhere there is that. That's
Yes.
as step number one. Yeah. Anyways, I tried to make that joke, but take continue, please.
Yeah, so now can someone,
Yeah.
Up and to
talk
it.
about the life of a different engineers in different sectors?
Sure. Well, let me talk about like things that would be common to all of them,
Hmm.
right? Which is reading the data sheet is like not going anywhere. Right? Again, talking about embedded engineers, you're either reading like a data sheet or you could be reading a data sheet to figure out what a particular peripheral or a piece of hardware does, how to program it, or what to expect from it. That is one. And it could be for the reasons of either testing it, validating it, or writing drivers for it. And if you happen to meet engineers who are like writing drivers, typically the OS environment would be given, right? They would either be working on like some RTOS, like free RTOS or VxWorks or something like that, or they would be working on top of what do you say, a heavyweight high level OS like, let's say, Linux, right? But in all cases, you're reading the spec sheet or the data sheet. You're reading lower level drivers related code, or you're writing that, and then you know yeah, pretty much. If you're an applications engineer, then you also kind of follow through and get it to be tested or get it to be run in the final shape and form. And yeah, so talking to people, reading spec sheets, writing code, reviewing code, yeah, all those stuff. In terms of what people do like differently in different industries, I think testing is something that varies from industry to industry. Or like the healthcare and the avionics and the automobiles are like code review and stringent, like the strictest form of code review, and what do you say, ensuring stability of the code, like that's the highest there. So the engineers in on that side of the world would be spending most of their time writing small pieces of code that are resilient, very deterministic, and are reviewed like in 10 different ways, put through like many systems, or what do you say, things like Misra C and all, right? You have to adhere to certain coding guidelines, so on and so forth. So yeah, those kind of things might differ from engineer to engineer depending on which field you are. But yeah, digging into what the hardware is expected to do through this data sheet, that stays. Writing lower level or systems level code, operating system types code, that stays. Reviewing, that stays. Yeah, that's what I can think of. Anyone else wants to add anything?
Yeah, so we can talk like what are the differences? Like you talked about the general aspect. I'll talk
Hmm.
some specializations.
Specific,
We
yeah, sure.
already talked like okay, automotive. If somebody is working on a software that is supposed to go into car, there is always like MISRA-C and many other safety related things. So there are like a lot of safety certification people need to do,
All
and a
right.
lot of the significant part of the job is to make sure that the code is able to handle all unknown situations.
Hmm.
And by handle, it's not like you're supposed to handle a situation where like the brake has failed, like you can't
Hmm.
really stop the car, but at least the job here is to notify that the brake has failed, so that the
Hmm.
user doesn't really go into the speed of 100 and then try to apply brake and then it doesn't work. So
Right.
by safety certification, the expectation is that you avoid any unexpected beer. That's everything comes down to it. Then there
Is
is
that
another
is
industry. Yeah,
Sorry,
go ahead.
Nikhil, is that called graceful degradation or graceful failures? Where it's not like catastrophic, but there is like an indication of like the system will go in bad state
Correct,
eventually.
correct. There's a term failure mode effect analysis, which is like a proper
Yes, yes.
standard procedure people follow where they think about various scenarios and
I
how we
see.
can like reduce the risk level by handling certain things in the software. And
Yeah.
everything comes down to just like notification or like haptic feedback
Alerts.
or something to
Mm.
say that something has failed rather than
Mm.
taking abrupt action. So that's
Yes.
automotive for you. Now there are cases where there is a lot of machines, robotics, industrial automation. So imagine there are like a lot of machines being controlled, and if there is like a three-axis robotic
Mm.
arm that has to pick up something, you are really making sure that all the three motors are in sync. So people there care a lot about latencies. So
Mm.
Hmm.
latency is like very every day and day out, people will be talking about latencies.
That's
That
true.
I'm able to send this command to this motor and send this command to this motor, and the time to respond between the two motors is like more than 100 microsecond. Now,
Mm.
that might be
Mm.
acceptable for few people, but not acceptable for people who are working in the industrial automation or robotics or
Mm.
anything. Anytime there's like motors being controlled and
Mm.
whatnot.
Mm. Mm.
Plus, there is like other field which is like IoT. A lot of people are working on IoT where there's a lot of network related things, and
Right.
most of the time you want to use like uh, open source stack or some ready-made tools to make your fancy things available, but it's a nice balance between what things you reuse and what vulnerabilities come with it.
When
So most of the time people are trying to either port some solutions, make it better safe, or they are trying to like solve some issues, security related things. And no, in general there's like development which is focused on trying
Mm.
to make multiple things interact together, interop together. Sorry.
Hmm.
Mm.
Yeah, so the
So that's
most of the
IoT.
so most of the startups are funded around started around IoT things
Mhm.
because it's simpler to start, and then you have all the things available at your disposal and you can make something useful, right? So
Correct.
But at least those are the startups we get to hear a lot about.
right.
There might
Yeah.
be like automation startups also, but you know,
I have a
at
point.
least
If you say that a startup, then the life of an embedded engineer might be much different because
way different.
because
Yeah.
it's a startup. The person is supposed to know what's going wrong in the microcontroller. At the same
Right.
time, he's supposed to fix a website also
Yeah.
because
Yeah.
Yeah. It's
so
like
that's actually very
it's
full
like
stack.
yeah.
It's full stack all the way through.
Yeah.
It's like a senior engineer saying, "I am the documentation." So
Yeah.
yeah.
But I've also seen a lot of embedded engineers actually be very proficient, like from like the controller all the way to the web technologies. That's
That's really full stack.
yeah, that's really full stack.
Yeah.
I've seen in a couple of cases. You and what happens is you can actually talk to these people about any problem anywhere in that stack, and they'll have something to contribute. Anyways, what I meant was it's very fulfilling to talk to such engineers. Yeah.
Yeah, I think to wrap up, I have one interesting and fun question to ask.
Okay.
How come an embedded engineer has more hardware on their desk than an actual hardware engineer? So,
Oh, interesting. Well, the hardware engineers make the RTL, and then they forget about it. They move on to the next
yeah,
project. That could be one. I don't know.
Yeah, so
Uh,
typically,
I
like the hardware design happens on a computer where you are working with tools and all of that. And as Piyush said, once the hardware is made, there's nothing they can do about it. So
Yeah.
it's up to software engineers to make sure that the software is I mean, there is like first half is done, and most of the hardware when it is manufactured, it will be sitting on people who are like software engineers,
Yeah.
their desk, and it is their job to get the software working and like apply any software workarounds, develop features and whatnot. So it's an irony that if you call yourself as an embedded software engineer, you'll be
You will
having
have hardware.
codes on your desk. But if you're like a hardware engineer or like design engineer, your
You'll be
desk
working on
is
Linux.
pretty clean. Yeah.
Yeah.
yeah,
So just adding a bit to it. The type of hardware these guys are supposed to work, the hardware engineer, those are either very big in
Yeah.
size
True.
or they have so much ESD restriction that these cannot be kept on disk. So either you
Yeah.
will find all these embedded hardware engineers, specifically like the one that work on the board design, etc. They will either be sitting in labs, or DFT engineers. They will be sitting in a much more secure lab, sitting downstairs where they have to put up sometimes suit as well
Yeah.
to
Yeah,
work with that hardware.
By downstairs, are you suggesting it's usually underground?
Lab
Or
factories.
factories? Okay, downstairs. Fine. Fair. Cool. That is
yeah,
there.
So they have different. They have a different hardware to work with.
Yeah.
right.
It's
Okay,
interesting how their hardware doesn't have wires coming out of it, and the machine that Rajat is kind of hinting at, that machine can only be placed in like a big facility, like a fab.
mm.
Yeah. Anyways, okay, go ahead, Dave.
Yeah. So I think I'll wrap it up if unless you guys have any point.
Nothing from my side.
So,
Okay.
just so that I'm not specifically hinting, I am talking about the automatic test equipments. If you want to search on the web,
Google
these
search.
in ATEs or in DFTs, they have like strip testers or something. These are like very expensive testing machines, which actually sometimes directly prop the packaged silicon to run the tests.
Also programmed by embedded engineers, by the way.
Yes, yes.
Yeah.
I think I should add one more point. Maybe not once a day or something, but in a lifetime, embedded engineers end up burning boards also.
Yes.
Yeah, yeah.
That also happens.
Yeah. Yet, thank you all for your inputs and thanks for whoever stayed this late. And then we also have a Discord channel and a WhatsApp channel where we do fun discussion and quizzes and whole lot of things.
Yeah.
So please do plan to join there if you find this conversation interesting. And see you next time.
Yeah.
Bye.
Take care, folks. Bye bye.
But
Yeah.